Okay, so we're going to get going, and we're going to dive right back into where we left off last time. We were talking about the way you build stacks so that you can call functions and recursively call more functions. So just to place yourselves in the stack of levels of representation and interpretation. We've been talking mostly about assembly code level, which is the human-readable form of machine code. And we were talking about how you write code to allocate space on the stack for a function call. Remember, in C, the programming language, there's two places you can store, at least two places you can store data, automatic and static. Automatic is the local variables inside a function. So every time you call a function, magically you get a new set of local variables that are only visible inside that function and only alive for the duration of that function. When you return from the function, they'll disappear. And those are allocated on the stack, right? And then we had static variables, which they live for the entire length of the program run, and they're allocated in static memory outside of the stack, just sitting there at the constant address during the whole run of the program. So we use this stack to hold these automatic variables. And one question people asked a few lectures ago was, if you only have 32 registers, how do you write big programs? Well, you just put stuff in memory. But the stack is one place where you can add more variables as you go along, local variables from your functions. So we give a name to this. Every time we enter a function, we create what we call it's called a procedure frame or an activation frame. It's sort of a defined layout of all the data we need for that one function invocation. And we mentioned last time there's a stack pointer, which is one register that is just one of the integer registers that by convention is used to hold the stack pointer. It's register 29 in MIPS, but in the assembly code we give it the symbol $SP because that's easier to remember than 29, I guess. As a second register called the frame pointer, which points to the start of the frame. And you usually don't need them. You don't need the frame pointer because the stack frames are usually a constant size. So you can just figure out, I can add to the stack pointer, then subtract from it to get back to where I started. But sometimes if you allocate variable-sized arrays on the stack, you kind of also need the frame pointer to know where you came from. And MIPS has a different register allocated to the frame pointer, $FP, to point to the first word of the frame. So if you look at, I'm at some point in the code here with a frame pointer here, a stack pointer here, and then I call a function. And when I call a function, one thing that function is going to do is set up its activation frame. The function knows that the caller cannot set this up because the whole point is the caller doesn't know what goes on in the subroutine. It's kind of hidden, abstraction. You hide inside the subroutine what goes on. The subroutine itself creates the space it needs on the stack. And so it'll move the stack pointer down. Remember, in MIPS, the stack grows to lower addresses. And it leaves space for these things. So in MIPS, the calling convention, there are 4 registers, A0, 1, 2, and 3, that hold arguments to a function. If you have more than 4 arguments, where do those go? Well, you actually have space on the stack. So the caller will actually push some arguments onto the stack before it calls a function, all the arguments that don't fit in those first 4 registers. You have 37 arguments to a function. 4 of them are going to be in registers. The other 33 will be pushed on the stack. And so the callee, the function you're calling, will know where to get the arguments. They'll just be at fixed offsets from the entry point here. Also, if this function is not a leaf function, remember a leaf function is a function that doesn't call other functions, right? So you have a call graph of A calls B, B calls C, C calls D. You bottom out at some point at a function that doesn't call anything else. That's called a leaf function. But any other function that's not a leaf, if it has been called from some place, there's a return address of where to go back to. You have to remember that, even though you in turn are going to call a different function, and it's going to have to know the return address. And remember, in MIPS, there's this jump and link instruction that overwrites the return address register, RA, which in MIPS is register 31. So when you do a jump and link instruction, the return address is placed into that R31 register. So if you've been called from somewhere and you're going to call a different function, you have to remember your version of R31 before it gets stomped on by you calling somebody else. So that's also saved on the stack. But remember, you only need this if you're not a leaf function. If you're a leaf function, you're not calling another function, you can just keep it in register 31. It's going to hang out there, fine. Remember as well, we talked about when you call a function, by convention, some of the registers are what we call caller save, and some of them are what we call callee save. So a callee saved register is a register that the caller expects to not be modified. And so if in the subroutine you want to change some register, you have to first save the old value, and then you can use it as much as you want inside the function, provided you restore that value before you return. And the place you keep those saved values is on the stack again, so there's space for those. And then finally, inside the function, you may need space for local variables, the things you declared inside your C function, and other objects are placed on the stack. And so this layout is, when the compiler generates your C code, it kind of figures out all the things that are going on inside each function and figures out the stack frame layout needed for that function, and that's sort of baked into the code it generates when it generates code for each function, right? So what the stack layout is going to look like. But there's a convention that's followed, and the reason you have a convention is, for one thing, that pieces of code that are compiled separately can call each other and, the things interoperate correctly. Also, if you're doing debugging, a debugger can step through and sort of backtrace what happened by following these things up the stack. It's called a stack trace, when you go back and figure out who called what. Now, a lot of you, using your laptop or whatever, you'll see that sometimes programs crash, and they say, do you want to send a report to Apple or Windows or to Microsoft, right? And what you might notice is in that report, there'll be a list of function names, and that's the stack backtrace, right? So that report that gets sent back to the developers is, how did I get to this point where things went wrong? And one of the things that gets sent back is, what is the call tree, the call path, and which function, where did I die, which function did I die in, and what were the arguments and all the calls that ended up at this function. So what that report is actually doing is, when something crashes, tracing back up the stack, recording that in a human-readable form, and shipping it back to the company. So when you're inside a function, then the code for a function, what it has to do to allocate the space is simply decrement the stack pointer, right? Just subtract the number of bytes you need to hold the stack frame, right? So you just decrement SP. So say we have a function like this. This is a function that returns an integer, has 2 arguments, but it calls a different function, this multiply function. So let's go to dive down on what the assembly code looks like. So we're hand compiling that C code into assembly code. So first thing we do inside this sum square code, so this is the C code, we allocate space for the stack frame. So we just decrement the stack pointer by 8. So this function only needs 8 bytes of storage on the stack. And what we're going to save in that activation frame are RA and A1. So RA is the return address, right? So because this function sum square is going to call this other function mult. And so I have to save the return address for sum square so I can get back to it. So it's going to put it in RA. It's also going to save the first argument. So this will be the Y value, right? So Y is in A1, X is in A0. Notice that this multiply function has 2 arguments. It multiplies any 2 values, but we're using it to do a square operation, right? So we actually want to create, when we're calling multiply, we want to put the same X value in A0 and A1. So what we notice is hey, this is great. A0 already holds X because I was called with A0 holding X. So inside this function, I don't need to copy it anywhere. It's already in A0, but I do need to place it in A1. So this is copying the value from X from A0 and putting it into A1. So notice now we're overriding that argument register, which is why we had to save it up here, right? We're overriding it here, okay? Then we do a jump and link to the multiply instruction, multiply function, sorry. So at this point, when the processor actually executes this code, it's going to go jump off to that function. That function is going to look something like this, but then at some point it's going to return. And when it returns, it's going to return to the following instruction after the jump and link. And here what we're doing is reloading the saved value of A1, which is Y. And we're reloading it because we needed to finish calculating the return value here. So remember, this function is mult, take the square of X and add Y to it, right? So we saved Y away in here, because it was in that argument register we overwrote. We restore it here by loading it back again into A1. Then we add it to V0. And what is V0? Right, it's the return value from the mult function. So remember, the convention is that A0, 1, 2, 3 are the 4 arguments to a function. Registers V0 and V1 are the values coming back from a function. So the return for the multiply, the return result here from this function call is in V0. We add y to it, just overwrite V0 again, because now V0 will then become the return value from this function, sum square, going back to whatever called sum square. Okay. Then, just to finish off, I have to reload the return address off the stack and restore the stack by adding 8 back to it, and then I jump to the return address to jump back to the original function. Okay. So that's how you translate that C function into MIPS assembly code, following this stack convention. Okay. Any questions here before I move on with that question? The question was, isn't RA one of those preserved registers? So why are you saving it here? Well, this is how you preserve it. This is what it means to be callee saved, is that the callee, the function here, is going to make sure it's the same when you get it back. So actually, no, RA is you return back to that. Yes, it will be callee saved. Yes, it'll be preserved because I'll load it back in and then jump back to the return address. So when I get back to wherever, so for example, here where I call multiply, this jump and link will write RA with a return address. Whatever it does over here, when it comes back to this point, RA will have the same value at the load word. At that point, RA will have the same value it had at the jump and link. But the reason it does is that the code at the other side saved and restored it. That's the only reason it does have the same values, because actually the callee was responsible for making sure that was true, and in this case had to save and restore it. If this function didn't call another function, it wouldn't overwrite RA, and you could just leave it in the register and it would just be the same when you did the jump register at the end, right? But it's the responsibility of the callee to make sure RA is not changed. Question?
Yeah, so if you had a nested function, would it be a separate stack altogether, or would it just add on new values onto an existing stack?
So this just adds on. So this, you have one stack and all the function calls just pile on the end. They just add on. So inside this multiply routine, it also just will decrement the stack further. But when it comes returns, the stack will have moved back up. So say I had 2 function calls. Say I called multiply here once, and say I called the divide routine next. The multiply would allocate stack frame. It would return, deallocate the stack. The divide would then allocate a different stack frame. It would reuse the same memory, but to hold different values, and then deallocate the stack frame, like this.
So what would multiply use as its return address? Would it use RA?
This multiply here, yes. So it has to, because the jump and link instruction in MIPS explicitly writes on R31. So this instruction, as we'll get to today, we'll talk about the encoding, how the bits are actually laid out in memory for the program. But R31 is an implicit destination of this instruction. So every jump and link overwrites R31. So you have to save and restore it, because this instruction is going to stomp on it. And RA will then have this value of the load word address. Question at the back? We'll talk about later today how you address them. Question?
Yeah, I don't know. I was just kind of confused. So I was looking to the D naught, you add that value and it saves like as a return address. But where do you actually, now I'm misunderstanding something, but where do you write like RA? That's where you want to store that value.
No, so RA is the return address. So it's a pointer to the instruction that you're going to jump back to. So this jump register RA writes to the program counter the value that you'd saved in RA. And that has the effect of causing the processor to jump to that address and start executing instructions there. V0 is the value that you returned, right? So RA is the return address of the code. V0 is the value, right? So like look at this. When I call this jump and link, I need to know the address of the multiply routine. And it's somewhere down here in program memory, down here somewhere. So I encode the address, I jump to here, but I have to keep track of what was this address of this instruction. So when I'm done with multiply, I'll make sure to jump back to where the load word is. And that's completely separate from the value that's returned, which comes back in V0. The result of the multiply comes back in V0, right? That's the value. RA is just the instruction pointer. Which instruction do I go back to? Question? Sorry, repeat the question. So at the end of mult, what would the jump? So how would you return for multiply? What would be the last instruction in the multiply routine? Right, exactly. So all the functions return with JRRA. So every function call is going to end with a JRRA. Jump to the PC whose value is in the RA register. All your subroutines are going to end that way. Okay. So if you look at a function so you can see this kind of a template. So the way the compiler works, it has a template of what a function should be compiled, how a function should be compiled. Then it fills in the template with the specifics of every piece of code you give it. And so every function has a label, which is basically the name of the function with a colon. So in the assembly code, you give it a label, and that's so you can symbolically, if I go back to this slide, I give a symbolic name for the function I want to call. I want to call the multiply routine. I want to call mult. I don't write out the binary address of the function. I just give its name. Because at this point, I don't actually know where it's going to be in memory. So I just have a symbol saying, when you're all done compiling and linking this jump and link should go to wherever this multiply routine ends up in memory. And in the assembler, which is this human readable form of the machine code, you can just use these symbols. I just say multiply colon means, assign to this symbol multiply the address of wherever this instruction ends up in memory, right? So then I can use mult as a placeholder for that address in program memory. So at the start of every function, you can have its name with a colon, and that's going to be a label any other function can use to call this function, right? It's going to know that's where it lives. Then there's going to be allocation of the stack frame. So the first thing you do is actual instruction you execute. Remember, the label here is just an instruction to the assembler, right? It's not actually going to end up in the program per se. It's just an instruction to the assembler to remember this is a name for this point in the code. The add here that decrements the stack pointer, that's a real machine instruction. It's going to be in the program memory and actually do some work when the code executes, right, and decrement the stack pointer. Then we're going to save any registers we need to first. Then we're going to actually do all the work we need to do. And then we're going to restore all the registers, including the return address, deallocate the stack frame, and return. So every function will have the same pattern to it, okay? Now this first part we call the prologue. And the last part we call the epilogue. Before you get going, this is all the prologue stuff you have to do. Then you do the actual thing you were trying to do in the function. And then you have the epilogue to clean up afterwards and return. Okay, so it's a standard structure in all the functions. So where's the stack in memory? So we already talked about this. In MIPS, it starts at the top of memory, high address, and grows down. The programs live in the bottom. Static data lives above the program text. So programs are often called text. It's just the convention. It's just the code segment. It's also called the text segment. It's where the program lives. So programs are different sizes. Your big programs, small programs, medium programs. So you don't know where the static data starts unless you know how big the program is. And you want to use as little memory as possible. So there's another register allocated in MIPS by convention to hold the start of the static data, right? So this is initialized before your program starts running, and it points to the first word of the static data section, right? And this is called GP for global pointer. So remember, the static data is data that lives for the entire life of your program, and is visible to all the code, right? And so that's why it's called global data, right? Just global static data. This global pointer tells you where in memory is the base of all that data, and then offset from that, you can generate load and store instructions to get at any individual one of those pieces of global data, right? Now the heap is the dynamic data. Remember, we have the stack for variables inside each function, static data for data that's just long-lived for the entire duration of the program. You sort of allocate it as the program starts running. Then we have the heap for dynamic data that you allocate and free as you go along. And remember, the heap grows and shrinks depending on how much data you're using. And objects in the heap are visible for varying durations depending on when you allocate them or when you free them. So here's a picture showing this. So we have, actually the program does not start right at 0 address. There's a little piece that's reserved here. And one of the reasons this is reserved is that it's illegal to access that piece of memory. So your program tries and touches addresses around 0, you'll get an error, a segmentation fault. And the reason they do that is a very common bug programmers have is using a value that's 0 as a pointer and trying to dereference it, right? Dereferencing a null pointer is a classic bug. And so by making the area around 0, off limits, you'll immediately detect when that's happened because the machine will just crash and say, look, you did something wrong here. You're trying to dereference, you're trying to access address 0. Well, that probably means you had a null pointer that you were dereferencing. So there's a little area here that's off limits. Then the program text lives here. Then the static data lives next. And this boundary, how big these pieces are, depends on the program you compiled. The heap then lives on top of the static data and grows upwards. The stack lives at the top of memory and grows downwards, almost at the top of memory and grows downwards. This is just halfway up the address space. Notice the hex address is 7FFFFF. So the high bit is 0. So this is actually 0, 1, 1, 1, 1, 1, 1, all the way down. There's actually another half of memory up here with the high bit set, and that's reserved for the operating system in MIPS. So those addresses are just off limits to the user program, the regular program that's running. That's kind of a detail you can ignore for now, but that's why we're only seeing half the address space, right? From 0 to 0 and all followed by all ones is that top address. So that's the memory layout, and we'll talk next time about the compiler and linker and how all that works to actually fill all this in for a program, builds the whole binary image that the operating system can load in and run as your program. It's just summarizing all these conventions. So as you'll see later when we design the processor, all the registers are the same. There's nothing special about any of the registers. You can use any one of them in the instruction. And it's just that in software, there's a convention about how you use the registers, and they're given names according to that convention. But the registers themselves are not special in any way. They're all the same, except that 0 holds the constant value 0. It's always 0, no matter what you try and do to it. And the other one that's a little special is the return address 31, because the jump and link instruction will always write to 31, right? So those are the only two registers that are somewhat specialized. All the other registers from 1 through 30, they're actually interchangeable, right? You can just use them for any purpose. But this is the convention that we have. So V0 and V1 are allocated to register 2 and 3. A0 through A3 are the argument registers allocated to registers 4 and through 7. The temporary registers, T0 through T7, 8 through 15, and so on. These are the more saved registers. A couple of temporaries are up here for some arcane reason, why they're not contiguous. And here's the global pointer, the stack pointer, and the frame pointer in these last few registered numbers there. So this is just a convention. You could come up with a different compiler that had a different convention. This is the one that MIPS uses as the standard for their C compilers. In fact, they have several different versions of this. This is the original standard. They've done some different ones since then. So it's just a convention. Okay. So let's, good, somebody spotted, where's register 1? So we'll find out about register 1 later. Where did register 1 go? Where did 26, you won't find out about that in this class. But so 26 and 20, so MIPS did a, 26 and 27 are reserved for use by the operating system. And if you try and use them, you can use them, but the operating system can clobber them at any time, is the answer for 26 and 27. So as somebody writing regular programs, you can't use them because you can't rely on them retaining their value. They're reserved for the operating system to stomp on. Register 1, we'll see later, is used by the assembler itself to make it a bit easier to write code. The register kind of needs a place to have a temporary for its own use, and so it uses register 1 for that purpose. Okay, so a minute trivia. Let's take a break here. So homework 2 is due on Sunday. Now, you should have got the email that told you what we're doing is, we know a lot of you had trouble getting through the homework 1. but a lot of you finished it. Great, all you that finished it. However, what we're going to say is you can resubmit homework 1 as what we're calling homework 1 prime. We're going to give it 80% of the weight of homework 1. And if you actually score better on that than your original homework 1 submission, it'll clobber the homework 1, right? So, if you did it on time, you'll get the full set of points. If you want a bit more time, we give you another chance to try. You won't get the full set of points, but you'll get most of the points if you do that. And we're not going to give you the auto-graded results until after homework 2 is due. The whole point is for you to test the code out. And you have to register your Project 1 team, you and a partner. Remember, they have to be done in pairs by this Friday. Okay? All right, so you lose EPA points if you don't get it done by Friday. Okay, now just quickly in the news. All right, so one thing I found, this is an announcement came out a few days ago. So Verbatim, you may know Verbatim from people who make DVD discs, Blu-ray discs, writable discs. They work with this company called Milanetia. Milanet, I know how to say it. And they just launched this thing called M-Disc, which is a 100 gigabyte Blu-ray, writable Blu-ray drive. But the big claim to fame is they claim the data on this drive will last for 1,000 years. Right? So, I don't know what the warranty is like. 1,000 years' time, it fails, you have to take it back, I guess. And they'll refund you. But it's a great thing as a company to guarantee. I guarantee in 1,000 years' time, we'll give you your money back if you try and read it. But this chart is actually in the marketing material. They compare the expected lifetime of, flash, like USB keys or flash drives or disk or tape, sort of 10-year kind of time frame. One thing to realize with flash drives is they're sort of non-volatile, but they're sort of not. They'll actually, you'll lose data eventually on flash SSD kind of drives. They just migrate away. Paper, they claim, is sort of 100, 200-year lifetime information stored on paper. I think that's actually pessimistic. We have documents going back, a couple thousand years that were stored on paper. So I think that's a bit pessimistic. But they claim, up to 1,000 years. And this is and the way this actually works is regular Blu-ray discs have a die on the front that the laser changes the composition of the die. And the problem is if you have UV light or other stuff, it can change back, and so you'll lose the data. These discs, they actually use a laser to burn the material. So actually, they create these pits on the surface. So it's actually a mechanical thing. And the cool thing about it is the laser they use to read the Blu-ray discs will read those pits the same way it reads the die change on a regular Blu-ray disc. So it's kind of like actually blowing holes in this material, and that's why it lasts for so long, as opposed to the die-based stuff of regular Blu-ray discs. Anyway, so in 1,000 years' time, we'll come check to see how they're doing on this. All right. Okay, let's take a 2-minute break. Okay, let's get going again. So, just sort of sitting here thinking about what movies people are going to want to watch in 1,000 years' time. 1,000-year-old movies will be stored on these things. Okay, levels of representation. So now we're going to dive one level deeper. So the last lecture or so we just talked about at the assembly language level, which is the human-readable form of the machine code. So the rest of this lecture is going to be in binary. So we're just going to do ones and zeros. Right. Basically, how you encode all those instructions in bits in memory for the whole program. So remember, this was one of those big ideas that happened in computer architecture right at the beginning, was the idea of a stored program computer. So this is the computer that stores the program as bits in memory. Remember, there was this big machine they built at UPenn, ENIAC, and it was very fast. It was the first all-electronic computer, but it was really fast, so fast, all the calculations were done in seconds. However, it took days to reprogram it because you had to basically rewire the thing when you reprogrammed it. So it's pretty useless in practice. And the guys who worked on it, Eckert and Mauchly, were the chief architects, plus a bunch of other people. They sat around and decided, maybe we should just store it as data in memory. So they had this working group. They were thinking through these ideas. A guy called von Neumann came to visit them. He was more of a logician. He, interesting ideas, wrote up a report about what had been going on in that group. And some overzealous clerk sent this report all around the world to everybody. And since then, this style of machine has been known as a von Neumann machine, even though he wasn't really the primary motivator at all for the work that got done there. And also, because this got sent out early, they couldn't actually patent the idea of a stored program computer. Anyway, the good news is the idea got out, lots of people built machines, and this is how everything works until today. So everything, the program is just bits in memory. Remember, everything is just, bits in memory. Instructions, data, it's all just bits. And every memory location, there's an address. There's a location associated with that tells you where it is, right? Now, you've heard a lot about C pointers. In the C code, those pointers, they're just a very light abstraction over machine addresses, right? They're just really the same thing as the machine address. One thing we haven't talked about too much so far is inside the CPU, as well as those data registers, the ones we were just talking about, those 32 ones holding values, there's another special register called the program counter, which points to which instruction am I executing right now, right? So inside the CPU, it points to where am I in the program. Now, historically, it's called the program counter. This came back from the calculator days where there was no branches, so you just run through the code. But it's really a pointer to an instruction. And actually, Intel calls it an instruction pointer, which is a much better name for it. But most machines call it the program counter, or PC. Now, the way you encode the programs in memory, so they live in memory, they have addresses, but what are those bit patterns? So the bit patterns of the instructions in memory, how you encode them is called the instruction set architecture, right? That's just the name, ISA. And when you distribute a program for machines, you distribute it in that binary format, and it's encoded for a particular ISA. So Intel x86, it's used in the Macs, Windows PCs. That has one particular kind of bit encoding. The ARM processors used in your iPhones or Android phones, or lots of other places, that is a completely different bit encoding. And so if you want to take your C code and run it on two different kinds of machines, you have to recompile, and the compiler will generate the appropriate bit patterns representing the instructions for each of those different ISAs. So the idea of binary compatibility is two machines are binary compatible if they can run the same binary programs, right? I can just take the compiled code and run it on these different machines, right? Now, back in, the midst of time, IBM at some point picked the Intel 8086 to build their PC around. Like the first IBM PC came out in 1981, and they just happened to pick this 8086 processor. It's a very interesting story if you go back and look at it. It was just a casual decision they made, which had massive consequences. And the reason was that IBM actually at that time didn't think the PC was that important, so they didn't lock it down in any way. They were using a processor they bought from somebody else. They used an operating system they bought from this small company called Microsoft. They put it all together. The BIOS, they made that open. And they used standard components. And it turned out that people could clone the machine very easily. So Compaq got started making clones of the PC. And so the whole PC industry arose because a lot of people could make machines that were all compatible and run the same programs, right? that kind of drove down the cost. If there was only IBM selling it, they'd be pretty expensive machines right now. But because of competition, because they're all compatible, all the programs run anywhere. That's because they all have the same instruction set. And so PCs from today can still run the programs that were written back in the early 80s because it was binary compatible. Okay, so in MIPS is a slightly newer instruction set. It came out in the mid-1980s, the instruction set. And it was part of this RISC wave. So the x86 is an earlier CISC wave, complex instruction set. So we're teaching you MIPS because it's a simple instruction set, and that was one of the design goals. So remember, in the MIPS instruction set, when you access data as load word, store word, it's in 32-bit chunks. There's also load byte, load half word to get 8-bit and 16-bit chunks. But instructions are actually all stored as 32-bit words in MIPS. So every instruction is 32 bits wide. There's a fixed width for the instructions, okay? That's one of the ways in which it's simpler than other machines. The x86 processors have instructions that range from 1 byte to 16 bytes. They're variable length. And that's a little bit harder to deal with in the hardware in the machine. Okay, so remember that we're going to be diving into ones and zeros. So this kind of assembly, add $T0, that is the human readable form, and that's designed to be fed into a program, the assembler, which then creates that binary code. The machine never actually looks at this textual representation. It only sees the ones and zeros, right? So in MIPS, you're going to map it down into a fixed 32-bit word of ones and zeros. Now, 32 bits is the whole word, but to define an instruction, we need several different fields. You can kind of see them as the different components of this assembly code. Do we need an opcode, like do and add? Then we need the operands. What are you adding? Well, I'm adding, 0 and 0 to T0, right? So I need to specify the operands and the operation. So those are different fields within that 32-bit word. So they're just, this number of bits tells you what operation it is. These bits tell you which registers to use, right? Now, you could have just one layout of instruction for every operation. It turns out that's not that efficient. So you actually want a few different formats of the same 32 bits, depending on what kind of instruction it is. So in MIPS, there's 3 basic types we're going to go through, called R, I, and J. Become clear why they're called that in a minute. So the I format is used for instructions that have immediates. Remember, immediates are like a constant that's built into the instruction. So I can add, 3, the number 3, to a register and store the result in the register. That 3 is actually stored in that instruction as a bit encoding directly, right? Another example is the load and store instructions can take an offset from a base register, and that offset is an immediate that's also stored in the instruction. So I format is used for instructions with an immediate, okay? Except for shift instructions, which we'll talk about later, okay? J format is used for jump instructions. So jump and link, those 32 bits are formatted a little differently, and that's the J format. The R format is used for all the other instructions that just operate on registers. So R is for register-based format. Okay. So let's start with the R format, because they're actually the simplest. So here's 32 bits along here, divided into these set of fields. 6 bits for the opcode, 5 bits for RS, 5 bits for RT, 5 bits for RD, 5 bits we'll use for shift amount, and 6 bits for the function. So RS is the first register source. So RS means register source. RT is another register source, and RT actually means register target. For some reason they called it something different. I would have called it RS1 and RS2. They called it RS and RT. So these are the 2 sources, the 2 values you read, and upon which you do the operation. RD is the destination register to which you're going to write the result. Okay, so there's 3 register fields in this instruction, 2 sources and 1 destination. This shift amount is a 5-bit value immediate that's used only for the shift instructions. So when you have shift left immediate by 3 or shift right arithmetic by 4, that number is encoded in this 5-bit field here. And finally, you have this 6-bit field on the end called funct, which is for function. And basically, there's not enough space in the 6 bits to encode all the different kinds of operations you want to do. And so there's more encoding space in this funct field down here. Okay, so the combination of the opcode plus the funct field tells you what kind of operation you want to do. Is this an add? Is it multiply? Is it a shift? That's encoded in these fields here, okay? So this is a 32-bit word. These 32-bit words are stored in memory. This is just telling you how that word is broken down into fields and where the different elements of the instruction are encoded in that 32-bit word. Kind of already said this. Question you might have is, why is opcode here and funct here? Well, you'll sort of see that as you work through all the different formats. Basically, you have to make things work well for all the formats, not just one of them. And so things end up being as a compromise about where you put stuff. And also remember, as far as the hardware is concerned, it doesn't really care that it's, it doesn't know that that's next to each other. That's just in the diagrams we draw, right? So the real hardware, they're just wires running everywhere. It doesn't really matter where things are laid out too much. Okay, I've kind of already said this. RS, source register, RT, target register, RD, destination register, okay? So that 5-bit field for the registers, that means it can specify any one of the 32, but remember that 0 means register 0, which is always 0. It reads 0, and if you write to it, the write is ignored. It will stay 0, okay? And that's important, as you'll see later. There are a few... MIPS instruction set is mostly pretty clean and orthogonal. It makes sense. It's very regular. There are a few exceptions. As in life, everything is mostly regular, but there are always exceptions. And here, the multiply and divide instructions are encoded a little differently in MIPS. And we'll talk about those later. And actually, it's probably best just to look in the book for this. So the shift amount I mentioned already is used for the shift instructions. So remember, we have a 32-bit wide machine with 32-bit values. So shifting by more than 32 doesn't make it all the bits disappear, right? So you only want to shift between 0 and 31 bit positions. So that needs a 5-bit field to encode. And it's just 0 unless you're actually doing a shift instruction. Now, I'm going to go through the different formats here just to give you an idea how it all works. But if you really want to study it, you should go look at the green card, what's called a green card insert, which is like all the instructions laid out on a simple reference card. So if you're assembly programmer, you can just reference this card instead of having to go look at a big manual. It's called the green card because remember I said, why is a byte 8 bits? It was because the IBM 360. The IBM 360 had a green card that laid out all the instructions. It was colored green. That's why it's called a green card. It's like a cheat sheet for assembly programmers. And there's one for the MIPS as well in the book you can use. Okay, let's just do some examples. So say you had this in the assembly code, add 10 and 9 and store them in 8. So add register 10 to register 9, store the result in register 8. So opcode is actually 0. How do I know that? Well, it's just what the designers of MIPS picked. They decided that add would be 0 in the opcode space. Just an arbitrary convention they picked. Funct is 32. Again, just a decision they made about this is how they're going to encode add. There's thousands of options they could have picked. They just happened to pick 0 here and 32 here. And remember, this is a very important convention because all the compilers and the assemblers, everything else, they generate this code. And the hardware is going to execute it. You have to agree on what the numbers mean, right? So this is just the convention between hardware and software, the encoding, so that the hardware knows what to do with the binary when it gets it, right? So RD is 8, RS is 9, RT is 10. Shift amount is 0 because it's not a shift. And if you see this laid out now, if I do it in decimal, so these are the values I'm placing in each field in decimal. I convert each decimal to the appropriate binary representation here. So this is the machine instruction, right? So I've taken that assembly language instruction, converted it to the fields, converted the fields to binary, packed them into 32 bits. This is what actually gets stored in the memory, and this is what the hardware actually works on. Right, so your computer's running programs, it's repeatedly fetching and executing these bit patterns. That's what it's actually doing. Question? Sorry, I didn't hear the beginning of the question. Could you repeat, please? So the question was, why have this separate field for shift that's only used for shifts? Right? It's a good question. You don't need to do it this way. there's various arcane reasons they did it related to when they were building the hardware. If they want to spread out the usage of the bits so that any one bit is not too heavily loaded in the circuitry, so it slows it down. That was the original motivation. It's kind of a weak reason to do it now, and you wouldn't really do it now. And there'd be better ways of encoding the ISA, but that was kind of why they did it. And as you'll see, the encoding is pretty sparse inside 32 bits. It's not like they're really trying to cram, millions of instructions in there. So they kind of be a bit relaxed about how it's encoded to make it easy to build the hardware. So, more recently people have become a lot more interested in making instructions denser so you can run on smaller devices and cheaper devices. By the time this was defined, they were worrying about, quite high performance machines. They weren't really worrying about how big the memory was. And they're focusing on making the machine simple so it could run fast. So again, there's many ways you can do this. This is just a convention for how software is encoded for the hardware to execute. And architects spend a lot of their time arguing about best ways of doing that, right? And, if you look at x86 versus ARM, for example, they're very different philosophies. But, your C program looks the same. It's just when it compiled down, very different bit encodings, right? So, okay, so this was in binary. It's a little hard to write 32 bits in binary, and display it. So usually you break it into hex digits. And this is just taking every 4 bits and relaying it in hex. So this is it in hex. If you wanted to, you could say, wow, this is an unsigned 32-bit number, so what's its value as an integer? Well, this would be its value as an integer, right? So if you actually loaded it from memory and used it in an arithmetic expression, that would be its integer value. So remember, again, the machine just stores bits. It doesn't assign a meaning to it. It's only the program that operates on the bits that decides what the meaning is. And the data is only an instruction if you try and execute it, right? So if you point the program counter at it and start running code, the hardware is going to try and interpret it, those set of bits, as an instruction, right? But they're just a set of bits in memory. That's all it is. So that was the R format. That was one format. That's used for all the operations, arithmetic operations, values in registers. There's also the I format, which holds instructions where one of the operands is an immediate value, right? Something that's encoded. So one thing, well, why didn't I just use the R format for that as well? That would make life simpler. Just have one format for immediates as well. The problem is that we only have 5 bits in the R format for register specifier. And that would mean your immediates can only be up to 5 bits wide. And it turns out that's quite often you need bigger immediates than that, so that would be kind of limiting. And so we provide a second format that has more bits available for the immediate. And one thing to realize is if I'm doing an add with an immediate, I only need one source register because the other source register has now been replaced with the immediate. So those 5 bits I was using for one of the source registers can be replaced, can be used as part of a longer immediate encoding, right? So this is the I format for MIPS. So again, overall it's 32 bits, but broken down into the same 6 bits for the opcode, the same 6 bits for the first register, but now the second set of 5 bits, although it's given the same name RT, is different in function. This is now the target, the thing you write to as the result, right? So this is the one source, and this is now the destination. And now the low 16 bits hold the immediate, right? So you can, in a single instruction, operate on up to a 16-bit immediate. And that immediate is either a signed or unsigned number, depending on the instruction, right? But it's a 16-bit value, right, that you can have in one instruction. So we'll talk a little bit about what happens if you want more than 16 bits, but inside a single instruction, you can have up to 16 bits of immediate, encoded in this way. Notice another thing that happened here is that we lost the funct field down the bottom, right? What this means is you only have, 2 to the 6 at most opcodes that could use an immediate, right? We kind of lost that other field that was specifying different operations, right? So generally, you have fewer operations that use immediates because you've taken up some of the space, encoding space, with the immediate field itself. Okay. I've said most of this already. All right, let's look at a few examples of instructions that use the immediate field. So add immediate, set less than immediate, set less than immediate unsigned. Now here's a tricky thing in MIPS. So in MIPS, for these instructions, the immediate is sign extended. So there's 16 bits in the instruction. The highest bit of that is the sign in this case. And sign extension is saying, well, I actually need a 32-bit value to work with the other 32-bit values in my register file. So what I'm going to do is take the high bit of here and just replicate it to fill out the top end of the word. So there'll be 32 bits now, where the top 17 bits are the same. The top 16 bits are just copies of the high bit of the low 16 bits, right? So the top 17 bits are the same. The top 16 are copies of the next bit down. One thing that'll be confusing to you and trips up everybody every time is that this instruction, set if less than immediate unsigned, treats the value as an unsigned value, but you got the value by sign extending the immediate, thinking of it as a signed value, right? So let's try and work through this. There's a 16-bit field in the immediate. It's sign extended. That gives you a 32-bit bit pattern to work with. The instruction, though, this instruction treats that bit pattern as representing an unsigned number, right? So if the signed bit was set and you had the high bit set in the number, it'd be a very large unsigned number, and that's how it works, right? So this is, you have to get in your head the difference between creating the number and how you interpret the number, right? Creating a bit pattern, and how does the instruction interpret the bit pattern? So set if less than immediate does exactly the same sign extension, but it thinks of it as a signed number in calculating whether it should be if you're bigger than or greater than, less than or greater than that number. Okay. So the same offset, the same 16 bits is used as an offset in loads and stores. And the reason they pick 16 bits, it turns out it's big enough to hold the majority of the immediates you actually need in programs, right? So it's quite rare you need an immediate bigger than 16 bits. And so this actually works out pretty well. One question you should have asked yourself right at the beginning is, why are instructions 32 bits? Why are they not 8 bits or 16 bits or 64 bits or 256 bits? Why are they 32 bits? And the answer is it's just about big enough to hold the right number of registers and the right size immediates. With experience, that's what people have picked. And it is a power of 2, which makes it easy too. So this is just another example of an I-format instruction. So here's an add immediate with adding -50 to 22, storing the result in 21. So how do you figure out the binary encoding? We look up the opcode. Turns out this one is 8. 22 is the source register. 21 is the destination register, the target register. And the immediate is -50. When you write out this in assembly code, the standard, if you don't say anything, then the immediates are all decimal, and the assembler will convert them to binary for you. So then let's just put this into the format. So 8 goes here, that's the opcode. Source 22, destination 21, immediate value -50. And in binary, you see this, because this is negative, it's held in 2's complement inside there, so the high bit is 1. This is assigned a negative number, right? So this is the bit 15. So 0 through 15, hold the immediate. And this is the same thing in hexadecimal, and this is if you treat this as an integer, what is its number? That's the number, right? So it's just bits in memory, just an encoding. Okay, let's see if you got all that. Here's a clicker time. So, down here is the information you need to know, which symbolic register name is mapped to which actual register number, and this is the opcodes and func values for these opcodes. And so these are different assembly instructions where you have to say which one of these instructions is the same bit encoding as the integer 35. Okay, let me start the... So try it by yourself first, then we'll give you a minute or two to chat to your neighbor. Okay, so going up for 2 minutes. A little bit of confusion there. So I think give you guys another 2 minutes to figure it out. Okay, so I think this time it's a clear winner. That's good. That's the right answer. So just go over this. So, I mean, a quick way of looking at this is, well, if it's going to be 35, that's a pretty small integer, right? In a 32-bit word. So most of the high bits are going to have to be 0, right? So, and the low bits, which are all in the funct field, so it should be 1 with funct equal 35. So it's going to be the subtract one. Now the question is, how do I make all the high bits 0? Well, it turns out subtract has opcode of 0 as well. That helps. Then RSRT and RD have to be 0. And shift amount is 0 because it's a subtract instruction, right? It's only non-zero for shift instructions. So I need RSRT and RD to be 0. And S0 is actually a symbolic name for register 17. So this would have 17, 17, 17 in these 3 fields. So this would definitely not be 35. So it must be this guy because all these bits are 0 except for 35 down there in the bottom. Okay? So quick encoding question. All right, let's go on to some more of the other features of the encoding. So how do you deal with large immediates? So 16 bits is usually fine, but sometimes you do need bigger numbers. So instead of, one thing you could do is say, well, I'm going to have a 64-bit instruction. So when you need a 32-bit immediate, I'm going to have a longer instruction where I have 32 bits saying use the next 32 bits as the immediate. That's one approach. Some machines work that way. The complexity there is the hardware then has to deal with 2 different lengths of instruction. So the MIPS deals with this by, instead of doing that, adding a second kind of instruction, which gives you the other 16 bits that you need. And this is called load upper immediate. So this instruction has a destination register and an immediate value. And what it does is, instead of treating that immediate as the low 16 bits of a value, it puts it in the high 16 bits of a register and clears the low bits, 16 bits of the register to 0. So it just initializes the high 16 bits of the destination with the immediate bit values and clears the low 16 bits. So I'll give you an example of how you use this. Say I wanted to add this 32-bit hex value to a register. Now, one thing you should say, well, this assembly code here this one line of assembly code looks like an instruction, but actually doesn't fit in one MIPS instruction, right? It's actually, the immediate's too big to fit in one of our 32-bit MIPS instructions with all the other bits you need. It turns out in MIPS, which is unusual actually, its assembler will expand this instruction, this assembly instruction, what we call a pseudo instruction because it's not really existing in the ISA, into multiple actual instructions. So we'll actually expand this, what looks like one instruction, into this code sequence, right? This is actually 3 real instructions that actually exist in the hardware implementation. So what happens is you do a load up immediate of the high 16 bits into this register AT. Then you OR in the low 16 bits. So the first one sets the top 16 bits. The second instruction sets the low 16 bits. And then you have a 32-bit value in a register that you can just add using a regular register instruction, right? So the assembler is expanding this one pseudo instruction you write into this sequence that has the same effect. So now you can see that's what register 1 is. So that $AT is assembler temporary, and it's register 1, and the convention is the assembler gets to use that for doing these kinds of tricks. So it kind of needs somewhere to put these values while it's working on them, and so the assembler reserves AT, the assembler temporary register, for this purpose, right? So this is something you get tripped up with a bit in MIPS. It's different than other machines in that what looks like one assembly instruction actually expands into more real hardware instructions at the bottom. And in writing your assembly code, only the assembler gets to use this $AT. If you try in your assembly code to use $AT, you'll find that weird things might happen because the assembler is doing these things and stomping on it behind your back. Let's take a look at branches, encoding branches. So MIPS, we have these 2 branch types: branch if equal, branch if 2 registers are equal, or branch if they're not equal. Okay? And remember, a branch, it checks that condition, but it also has to specify where to jump to if the condition is true. Right? Where do I branch to if it's true? And that's actually encoded using a 16-bit immediate. So this is also an I format instruction, right, with 2 registers and an immediate. But in this case, the 2 registers are both sources. They're both just read, and then they're compared. Are these 2 registers equal or not equal? That's the comparison being made. So then in designing this instruction set, the architects are thinking, well, what's the best way of using that 16-bit field to specify where to jump to, right? Now, something to think about, how a branch is used. Well, a common case is if then else. Like, if this is true, do this thing in your high-level code, or do this other thing. Another common thing is loops, where I have, repeat, do a for loop. So that's typical places you'll use branches. And those are generally small extent. You're just branching around locally inside a single function, right? There's not a large space you're trying to jump to. If you're trying to call lots of different functions, that's using a jump or a jump and link. That's a different kind of instruction. Branches are these conditional execution, and they're usually inside a single function. So the extent is pretty small, actually, for branches. The other thing to realize is there is this program counter telling you where you are right now in the instruction text. And so the idea here is to use what we call PC relative addressing. So instead of encoding the absolute address of where you're going to jump in that immediate, you're going to encode an offset from the current program counter. So plus or minus from where I am right now, that's where I'm going to jump to. So jump ahead by 10 bytes or 16 bytes, or jump backwards by 128 bytes. So you're going to use that immediate to code an offset from the current program counter. And so the immediate is a 2's complement value. So the question is, well, how far can I jump backwards or forwards from the current location, right? So you have 2 to the plus or minus 2 to the 15, because it's 16 bits with a sign bit, right? That's the range. Now, the thing to remember is MIPS is a byte address machine, so every byte has a unique address. every 8 bits. And instructions, though, are 4 bytes long, right? But one restriction we put on instructions to make it easy to build the hardware is those instructions have to be 4-byte aligned. So they can only start on byte addresses that are multiples of 4. So you can have an instruction starting at address 0, 4, 8, 12, 16, but you cannot have an instruction starting at address 3, right? That just wouldn't work. That'd make it too hard to build the hardware. So the instructions have to start on a byte address that's a multiple of 4. So we can use that to make the immediate go further by saying that we'll take the immediate, multiply it by 4, and so you should think of the immediate field as specifying how many instructions, plus or minus where I am now, should I jump to, okay? So if the branch is taken, jump to this many instructions forward and back, or you can think of it as in bytes if you multiply it by 4, right? So now the immediate specifies words instead of bytes. Now we can jump further around the target. So remember with the branches, if the branch condition is false, the branch does nothing. You just fall through and move to the next instruction. It's only if the branch condition is true, you're going to jump to this target address. So if the branch is not taken, you just jump to PC plus 4, just move down to PC plus 4. If you do take the branch, it's in MIPS, one little detail, it's not PC plus the offset, it's PC plus 4 plus the offset. So the offset is not relative to your PC, the PC of the branch, it's relative to the PC of the next instruction after the branch. And when we do the implementation later, you'll see why they did this. It's just a small detail, but it makes the hardware a little bit easier. Okay, so that's how they encode where the branch goes to inside that 32-bit word. It's a PC relative offset from the current location. So here's a little example. Here's a loop. I check some condition at the front. If these two guys are done, then equal, then jump to the end. So remember, this is assembly code that gets translated into this bit encoding. And this loop, I have a jump that goes back to the start of the loop. So this branch has opcode of 4. How do you find that out? You look in the encoding sheet. Register 9, register 0. You're comparing these two. You're comparing if register 9 equals 0. And the immediate then should be set to what value to get a taken branch to go here. Well, so remember the offset is relative to the next instruction. And then there's 1, 2, this is 3 instructions down, right? So I have to branch forward by 3 instructions. So that immediate is 3, right? So the offset is in terms of number of instructions. It'll be multiplied by 4 to give you the byte address. It'll be 12 bytes ahead, but that's 3 instructions ahead. So that's the value placed in the immediate field of the branch instruction. So look at it, and this is the 32 bits laid out. Here's the opcode. Here's one register specifier. Here's the other register specifier, and here's the offset. And that's it in binary. Okay. Now a question. See, I write my routine, and I compile it. I compile this 1C function. In a separate file, I have a different function. I compile that. And I have a library of pre-compiled routines. Then I link these all together to make my program. When I did that first compile of each file individually, I'll create those branch offsets. Do I have to change them when I link them all together? Do I have to change the relative offset when I link all the components together to make one big program image? No, I don't, right? Because it's PC relative. The branch doesn't care at which absolute memory address it ends up at. Right? This same routine could be placed at many different actual memory locations. It doesn't matter because it's PC relative, right? So that code is position independent. It doesn't care where it ends up in real memory. So one little trick is, well, what happens if I need to jump further than I can encode in that 16 bits? Well, it's a very simple trick. What you do is jump over a jump, and we'll see that jumps have a much greater reach than branches, right? So you can conditionally jump around the jump that actually goes to the target location, right? So if you can't do it in one step with the branch, then just go use a jump instead to get further reach, okay? Okay, so then we've done R format instructions and I format instructions. The third one we're going to look at is J format, and these are used for jumps. So branches are these conditional things that live inside functions And so the amount of code you need to branch over is usually pretty small. However, jumps and jump and links are things you use to connect functions across the whole program, and so you might have to jump quite a large distance in the code. And so, ideally we'd want to be able to jump anywhere in the whole, memory space. So you'd want to ideally have a 32-bit offset, so I could jump to any address in my 32-bit memory space. But we can't actually fit, the address and the opcode inside 32 bits, right? So we're trying to make every instruction be 32 bits wide, so we can't actually fit a 32-bit address inside a 32-bit instruction together with some opcode information about it's a jump, right? So what they do in MIPS is the jump format, you try and get as close as possible to doing that. So all they do is say only two fields. One is the opcode, and all the rest of the bits are used for the target address of the jump. So why doesn't the jump need any registers? Why is there no registers encoded in the jump format? The branch had 2 registers. Why doesn't the jump need any registers? Yep. So why don't you need the registers? Right, okay, at the back. Let me ask you a little different. So what's different between a branch and a jump? Yep. Right. So a jump is unconditional. Like, I'm going to jump regardless. At this point in the code, go there. There's no condition to be checked, right? So there's no values to read. You just know, just go straight to this location, right? So, go straight to go. Do not pass go. Do not collect $200. Go straight to jail. Right? You just go straight there. So they want to use the largest. So try and use all the bits as possible to make this jump, so you can have the largest programs possible. The other trick is that as you see, we're still jumping to an instruction, and those are word aligned, 4-byte aligned, so we can still do the same trick of multiplying that by 4 to give the byte address, right? So you do it in units of words, instruction words. So that gives us 28 bits. So notice back here we had 26 bits plus the 6 bits of opcode. So if you multiply this by 4, we've got up to like 28 bits of the 24-bit, 32-bit address space. So we're still missing the 4 highest order bits. And in MIPS, there's a little funky thing where they take the 4 bits from the current program counter and just jam them in at the top. So it's not added in, it's just jammed in. The top 4 bits are jammed in, and the bottom 28 bits come from the instruction, right? So it's sort of kind of PC relative, but not really. And in practice, it means that the programs are really restricted to the 28-bit space, which is pretty big for programs. You're talking, 256 megabytes. It's pretty rare to encounter a program where the program itself is greater than 256 megabytes. I think I've seen some that are like 100 megabytes, 110 megabyte programs, but 256 megabyte in a single application is pretty rare. But it is possible to have bigger ones. And if you need more than that, you can just use 2 jumps, or use a jump register where you build up a value in a register and then jump to it. Okay, if you need to jump even further. Okay. So this is just explaining how the target address is constructed. So it's the 4 bits come from the program counter of the instruction after the jump. So PC plus 4, take those top bits, 4 bits from that value, place them at the high end of the target address. The next 26 bits come from the field in the instruction, and the low 2 bits are 0, because all the instructions are word aligned. Okay, so just to go back over this thing I said before, the MIPS assembler does this thing of having pseudo instructions, which aren't real instructions, but expand into the real instructions. And they have some of these which are convenient shorthand for even if they are a single instruction. So for example, you have a move instruction in the assembler. There's no real move instruction in the hardware, But move one register to another is just shorthand for saying add 0 to the source and place it in the destination, right? So that form of that instruction has the same effect of just copying one register to another. You just have a assembler shorthand for that instead of having to type the 0 every time. Okay. And there's a large number of these in MIPS, and there's a wiki page that has them all on there. Some of the other ones you're going to hit are load address of a label. So this one you couldn't actually type in by hand. It's saying that somewhere else I've specified a label. I want to have the value that eventually becomes loaded into a register. So that's a load address instruction, pseudo instruction. Excuse me. Load immediate loads an immediate into a register, and it may load a large immediate in multiple instructions. Excuse me. We talked about this already, the AT register. This is reserved for the assembler. And so there's this concept of, there's MIPS, there's the actual MIPS true assembly language. It's really the machine code. And then there's this assembly level thing, which is what humans write. And that's been done to make it easier to write and read that assembly code. But it's not one-to-one with the actual code. Okay, so to summarize, these are the 3 formats. This is actually how the hardware sees software. It sees it as chains of these 32-bit binary words in memory. Okay? So see you next time. Wednesday.